Welcome to CoFeel 14. We are from the Faculty of Engineering at the University of Peradeniya. Join us on our journey to unlock the full potential of heat pumps. Follow CoFeel 14 for updates on our research into accurate heat transfer coefficients for mini-channel evaporators. Together, we can pave the way towards sustainable and energy-efficient heating solutions. Between 1986 and 2003, Sweden experienced a big increase in heat pump usage. But this caused problems like complex systems, high costs, and environmental issues. Professor Premal Fernando worked on ways to solve these problems by studying how to use less refrigerant in small heat pumps, 5 kilowatts, using data from experiments on mini-channel aluminum evaporators to figure out how heat moves. Here we are going to find the local heat transfer coefficient of a mini-channel aluminum evaporator. Let's dive in and uncover the secrets of efficient heat exchange in this innovative system. This is a pictorial view of the mini-channel aluminum evaporator. Glycol flows in the shell, while propane flows inside the tubes. There are 30 tubes, each with a length of 661 millimeters, arranged in 2 rows and held in place by 31 equally spaced 1 millimeter thick aluminum baffle plates. The ends of the tubes are fixed to 2 aluminum end plates. We have temperature measurements along the evaporator using glycol. If we take input as 0 length, temperature is taken. In that way, we have temperature measurements in glycol. We have only inlet and outlet temperatures of propane, but we have outlet and inlet pressures and differential pressure of propane along the evaporator. When we talk about the methodology, we use the pH diagrams to establish the relationship between glycol and propane. Here, we consider each small part along the evaporator as a small heat exchanger. Then, we can perform calculations for the propane. In the calculations part, we attempt to determine the mass flow rate of the propane using the heat balance equation provided below. Afterward, we can obtain the relevant enthalpy values for the propane.
First, the mass flow rate of propane was calculated for each section. Then, the enthalpy values for each section were determined. This process was repeated for all 248 experiments. A polynomial curve was assumed as the best fit to represent the temperature variation of glycol. Afterward, the 2-phase length was calculated for each section. Finally, the propane temperature variations were calculated, assuming 2 different linear variations, one for the 2-phase region and another for the superheated phase. Several properties should be found to calculate the tube side heat transfer coefficient at each section. The online tool called Fluid Property Calculator was used to find the properties of glycol such as enthalpy and temperature. Physical properties such as total outside area, inside area, total base area, total fin outside area, and no of baffle plates inside each sections were calculated for each section. Now, it's time to calculate tube side heat transfer coefficient at each sections using these equations. That's how the logarithmic mean temperature difference, LMTD, was calculated considering the end node's temperatures of the section. After that, the overall heat transfer coefficient, the shell side heat transfer coefficient, and the tube side heat transfer coefficient for each section were calculated using the equations mentioned here. This is the graph of one of the experiments showing the relationship between the shell side heat transfer coefficients and the sections. The coefficient value for section 1 is very small. Then, it increases to a peak and drastically decreases. This indicates that the heat transfer decreases significantly. Now, let's look at the comparison of the experimental results with the correlations. The correlations used are Lazarek and Black, Malek and Collin, and Pierre and Cooper. The corresponding equations are also presented here. Finally, graphs were constructed between the experimental local heat transfer coefficients and the local heat transfer coefficients from the correlations to identify the best correlation.
Investigating the local heat transfer coefficient of mini-channel aluminum evaporators has broad implications across industries. Enhanced local heat transfer coefficient improves efficiency in refrigeration and air conditioning, electronics cooling, automotive cooling for electric vehicles, food and beverage temperature maintenance, and precise control in the medical and pharmaceutical sectors. Additionally, it enhances efficiency and product quality in chemical and petrochemical processes, while supporting lightweight cooling systems in aerospace applications. This exploration opens avenues for innovation and efficiency across diverse industrial sectors. Thank you for watching.